Let's talk about independent and dependent events and the probability that they will occur. An independent event, or independent events, do not have influence over the outcomes of events. So one thing happening does not affect the likelihood of the other thing happening. And as an example here, flipping a coin, heads or tails, has no effect on the outcome of rolling a dice right after that. You're still going to get a 1 through a 6. If you flip a coin and get a head, it's not more likely that you're going to roll a 3, 4, 5, or 6 instead of a 1 or 2. They do not have any effect on each other whatsoever. But dependent events do affect each other. So the outcome of one event can affect the outcome of the other event. So the fact that one thing has occurred changes the probabilities of how the next thing will occur. And usually this has to do with a sequence of events that are repeated. But drawing 3 names from a hat is a dependent event. Because if I take a name out, that changes the probability of the names that are still in. They're all more likely to occur now. So the probability changes as this progresses. For flipping a coin, you always have a 1/2 chance, a 50-50 chance of getting a heads or tails. For a dice, you always have a 1 in 6 chance of getting one of those faces. Okay. So the probabilities, how we calculate the probability of these occurring, is also different from one to the other. Now, independent events, because they don't actually affect each other, we can just multiply their probabilities. So the probability of independent events occurring is the probability of the first event times the probability of the second event times the probability on down the line. Just multiply them straight together if they are independent. But the probability of dependent events gets a little trickier. So it's the probability of A and multiplied by the probability of B given that A has occurred. And this is the hard one to figure out sometimes, but we'll see some examples. So the probability of A is just what's the likelihood that the first event described happens. And then the probability of B given A is the probability that event B happens given that event A has occurred. Okay. Now sometimes they'll give me this in the problem, but a lot of times we have to diagram it out like we did with compound probabilities. So we would look at the probability of A happening. So we'd say, well, A could do this or this, and we know that, let's say, this occurred. So we're on this path. And then we would look at the probabilities for B, and we would just kind of follow it. I mean, you'll see how this works as well. So we would multiply this, and this would be our answer. So we would follow that diagram to get those percentages, and I'll show you that when we do the dependent events one. But these are our formulas. We're going to multiply for independent events, and then for dependent events, we're going to have to find the probability of the first event described occurring and the probability of B given A, which a lot of times will probably include this diagram. So let's go look. This is independent events. It says, if you flip a coin and roll a 6-sided die, what is the probability that you will flip a tails and roll at least a 2? So we need to know the probability of a tails. And for my second probability, the probability on a die that I roll at least a 2, which is a 2, 3, 4, 5, or 6. So we want probability of greater than or equal to 2. Well, on a coin, the probability of a tails is 1 success out of 2 possible outcomes. Could be heads or tails, so 2 outcomes. One of those is the desired outcome. The probability of getting at least a 2 on a 6-sided die, well, there's 6 sides, so that's my total number of outcomes. And of those sides, 5 of them are at least 2. 2, 3, 4, 5, and 6. So 5 out of 6. And since these are independent, I know that the probability of both of these occurring is just the product of these probabilities. 1/2 times 5 over 6. So 1/2 times 5 over 6, and that would be 5 multiplying top to top over 12 multiplying bottom to bottom. So we do 5 out of 12. Five out of 12. I'm going to go ahead and find the decimal of that as well. Sometimes it's easier to see what's going on. That is 0.416. Or 41.7% of the time. So if we had a tails, not a tail, excuse me, if we had a coin and a die, and we flipped the coin and rolled the dice, 41.7% of the time we'd get a tails and a number at least 2, or that's what we would expect to see. Fairly simple, just multiplication. Let's do the next one. So, Anton Jameson is shooting free throws. Making or missing free throws does not change the probability that he will make his next one. And he makes his free throws 73% of the time. So the probability of making it is 73% or 0.73. Which means the probability that he will miss, you can only have 100% probability total. So if I want to find the probability that he does not do something, I just take it away from 1. 1 minus 0.73 is 0.27. Which tells me that Anton misses his free throws 27% of the time. What is the probability of Anton making all of his next 9 free throw attempts? Well, they told me that making or missing his free throws doesn't change the probability. So that tells me they're independent. So all I have to do is multiply the probability of making it 9 times, which is an exponent. Repeated multiplication is an exponent. So we're going to do the probability that he will make it 9 times, which is 0.73 to the 9th power. So we just have to find that. Not 9 times 0.73. That's not what we're looking for. Not this. It must be that last one down there that has been cut off. Yeah. 0.73. 0.73 to the 9th power is taking the probability that he will make the shot and multiplying it to itself 9 times. So that's the one we want there. Captain Kevin has a ship, the HMS Khan. The ship is 2 furlongs from the dread pirate Ben and his merciless band of thieves. The captain has a probability 3/5 of hitting the pirate ship. The pirate has only one good eye, so he hits the captain's ship probably 1/5. If both fire, what is the probability that the captain hits the pirate ship, but the pirate ship misses? So we want to know the probability that Captain Kevin hits and Pirate Ben misses. Now, if they fire at the same time, then one cannot affect the outcome of the other. The cannonballs are already in the air. So these are independent. Whether Captain Kevin's cannonball hits or misses has no effect on whether Pirate Ben hits or misses. So this can just be the probability that Kevin hits times the probability that Pirate Ben misses. So look, they told me the captain has a probability of 3/5 of hitting the pirate ship. So that's exactly the probability that we're looking for. Although if he hits the pirate ship 3/5 of the time, he will miss 2/5 of the time. The captain has a probability of 1/5 of hitting the ship. But we want to know the probability that he misses. The probability that Pirate Ben will miss is 4/5. So then we would just multiply those together. We would end up with a probability of both of these events occurring as 3 times 4, which is 12, top to top, bottom to bottom, out of 25. So 12 times out of 25, this is what we would expect to occur. That's exactly what we get. And then this last one, if you flip a coin and roll a 6-sided die, what is the probability you will flip a heads? Well, we know that the probability of getting a heads is 1/2. There are 2 sides on a coin, only one of them is heads. And roll an even number. The probability that we roll an even number, that could be 2, 4, or 6, is 3 out of 6. But we can reduce that. 3 out of 6 is just 1/2. So we could do the multiplication with the 3 out of 6, but we're going to use the reduced one. If we do this, we get 3 out of 12. In the reduced form, we get 1/4, which is the reduced form. So it doesn't matter, but 1/4 is our probability, or 25%. Yep. So independent events, as long as one outcome does not affect the probability of the other outcome occurring, they're independent. You can just multiply the probabilities to get the likelihood of them both occurring. Now, let's do some dependent events. All right. So, Captain Ishan has a ship, the HMS Crimson Lynx. The ship is for blah, blah, blah. Pirate Michael and his merciless band of thieves. Okay. Then we have these probability breakdowns. We're going to have to use a tree for this one. If his ship has not been hit, Captain Ishan has a probability of 2/5 of hitting the pirate ship. If his ship has been hit, he will always miss. If his ship has not been hit, the pirate has a probability of 3/8 of hitting the captain's ship. If his ship has been hit, the pirate will always miss. So we know if the captain and the pirate each shoot once, but now instead of shooting at the same time, they're going to take turns for some reason. The captain shoots first. What is the probability that both the captain and the pirate hit each other's ships? So we want to know the probability of the captain and the pirate hit. However, these are conditional probabilities. If the pirate didn't hit the captain's ship, then the captain will hit 2/5. But if the pirate hit him, if the captain's ship has been hit, he will always miss. Okay. So we need to figure out the probability that the captain hits And we're going to multiply that by the probability that the pirate hits given that the captain hit. So the probability that the pirate hit given, that little vertical line is a given, the pirate hit given that the captain hit. Now, we know the probability that the captain hits. If his ship hasn't already been hit, the captain Nishan is probably 2/5 of hitting. So 2/5 is this first probability. But they didn't tell me the probability of the pirate hitting. We know the probability that he will hit if he hasn't already been hit. Well, we do. If the captain hit, this is going to be missed, so 0. Because if the pirate ship has been hit, Dread Pirate Michael will always miss. So 0, and 0 is going to be my answer here. But here's how I would diagram this out. Start out with the first event. The captain fires his shot. He's either going to hit or miss. So the captain either hits or misses. He has a 2/5 chance of hitting, which means he has a 3/5 chance of missing. 3 out of 5 times he's going to miss. Then the pirate will fire his shot, which we now have 4 possible outcomes from. Either the pirate hits or misses for both of the captains, because the captain shot first. So then we have these. Now it tells me if his ship has not been hit, so if the captain misses, then the pirate has a 3/8 probability of hitting. So we're going to put that 3/8 here, which means 5/8 goes here. If his ship has been hit, he will always miss, which means if it has been hit, this is a 1 and this is a 0. He's never going to hit. So now we can look at the probability of these things occurring. The probability that the captain will hit and the pirate will hit is 2/5 times 0. So that's never going to occur, which is this one, 2/5 times 0. Both of them hitting is not possible given the likelihoods. This one will happen 2/5 times 1. So 2/5 of the time, the captain will hit and the pirate will miss. Now, the probability the captain misses and the pirate hits, that's 3/5 times 3/8, which is 9/40. And then the probability that both of them miss, probability the captain misses and the probability that the pirate misses would be 15/40. And if you add all these up, you get 100% of the probabilities. Now, this one was pretty easy because we had the information, but as I work through these, I may need to diagram out how these occur. So I start with how many ways can the first event occur? So in this case, the captain had 2 possible options. He either hit or he missed. And we knew the probabilities of those, so I listed them now. Then the pirate. For each of the captain's choices, the pirate also had 2 choices. It's very much like the conditional or the compound probabilities. Hit, miss, and then we just worked it through there. In this case, though, the probability that both the captain and the pirate will hit each other is 0. It's just not going to happen. A bag contains 6 red balls, 4 green balls, and 3 blue balls. If we choose a ball, then another ball, without putting the first one back in the bag, what is the probability that the first ball will be green and the second ball will be red? So, we want to find the probability of getting a green, then a red. But because we are not putting the first one back, just like taking names out of a hat, we are changing the probability of the second event. The first one's easy. We can find the total number of balls just by adding. So there's 6 red balls, 4 green balls, and 3 blue balls. There are 13 balls in the bag. Of those 13, 4 of them are green. So the probability of getting a green ball is 4 out of 13. But now that first ball is gone. So after the first draw, the number of balls in the bag, this denominator for our probability, has decreased by 1. So the probability of getting a red, given that the first was green, is going to be 6 out of 12. Because the probability changed if I know that the first ball was green. The number of red balls hasn't changed. It's the total number that has changed. Then we just multiply those together. Doing a little reducing first, so the 4 and the 12 go together nicely. And the 6 and the 3 can actually reduce there. That just makes that 2. And it would be 2/13. 2 out of 13 trials will get you 1 green ball and the second one red, even though red and green make up the majority of that. Okay. Which is why sometimes, even though something seems very possible, doesn't mean it is. Mind, there are 10 green and red balls. So the probability of getting a green and a red ball is pretty high. But the probability of getting a green, then a red ball is not. And that's how gambling works in Las Vegas. They just stack the probability against you. They make it seem like you can win, but in reality, you cannot. All right. We'll keep working these just so you have examples, but in a class of 10, there are 2 students who forgot their lunch. If the teacher chooses 2 students, what is the probability that both of them forgot their lunch? Okay. So we want to know the probability of choosing 2 students where both of them have no lunch. This may seem independent at first, but we have to pick the first student, take him out, and then choose the second student, and they both have to have no lunch. So it is dependent because, like the last problem, the total number changes, and that changes the probability. So the probability that the first student has no lunch that one's pretty easy. It is 2 out of 10. The probability that the second student has no lunch given that the first student didn't about it. So there is now, since we've taken the first student aside, there's now only one student in the main group who doesn't have lunch. And the group is now 9 students. So this would be 1/9. And we would just multiply those together. So 2 times 1 is 2. Well, we can reduce this. That's 1/5. Let's go ahead and do our simplification. And then we can see 1 times 1 on the top would be 1. 5 times 9 on the bottom would be 45. So it's fairly unlikely that the teacher will be able to randomly select the 2 students without lunch. Yeah. And probably both. Because it is a dependent event, I found the probability that the first student had no lunch, and then the probability that occurred with the second student as well, given that I had already chosen that first student with no lunch. This one's another captain one, so let's see. I'm going to diagram this one out first. So the captain and the pirate each shoot once. The pirate shoots first. So the pirate shoots first. And he can either hit or miss. The probability that the pirate will hit, 1/7 hitting. So if her ship hasn't already been hit, Dread Pirates has a 1/7% of hitting, so 1/7 chance of hitting. If her ship has been hit, she will always miss. But she has a 1/7 chance of hitting, and then which means she has a 2 out of 7 chance of missing. Oh, excuse me, 6 out of 7. 2 out of 7 wouldn't make any sense. That's not 100%. So 6 out of 7. Okay. This is the case. If her ship hasn't already been hit, which means she is either firing first or the other person missed, she has a 1 in 7 chance of hitting, which means she has a 6 in 7 chance of missing. Then, our captain gets to fire. And from there, the captain could either hit or miss, hit or miss. Okay. So we look, if the captain's ship has not been hit, so if the pirate misses, then the captain has a 3/4 chance of hitting. If his ship has been hit, he will always miss. 100% he will miss. 0% chance that he will hit. Here, there's only a 1/4 chance that he will miss if his ship has not been hit. So let's go through and find these probabilities now. The probability, so here, this is the probability that both hit. Is 0. Even though this is 1/7, 1/7 times 0 is 0. The probability that the pirate hits and the captain misses is 1/7. 1/7 of the time, 1 out of 7 trials, that's what's going to happen. Okay. The probability that the pirate will miss and then the captain will hit is going to be, well, let's do that one. Let's calculate that out real quick. 6 out of 7 times 3/4. We just follow that tree. So 6 out of 7 times 3/4. 9/14 when we reduce. So 9/14. And then this one is the probability that the pirate misses and the captain misses. And we can see that's 6 out of 7 times 1 out of 4, which is 3/14. So the most likely thing that will happen is that the pirate will miss and the captain will hit. 9 out of 14 times, that's what's going to happen. So if the pirate knows this, if he has some statistics on who he's up against, he will know that head-to-head, probably not the best, because he's likely going to miss and the captain's probably going to hit. So he'll need to devise some other strategy to take that. But we want to know, if the captain and the pirate each shoot, the pirate shoots first, what is the probability that they both hit each other's ships? And I don't know why it keeps asking for both hits when it also tells me that somebody always misses. That's 0. They're not both going to hit. That would be impossible. All right. Yay. All right, guys. Keep working on the probability. You should be able to get quiz 1 done by this weekend. And then we'll move on to the other statistics as we go. What is the next unit after this one? Oh, permutations and combinations. Those are nice. That's a formula. So we'll look at that next week. All right. See you next time, guys.